Welcome to the BKR chemistry classes. Let's see what is spin splitting. To start with, I have taken an example of halo derivative. So this particular compound has two types of signals. As you can see here, I have signal A for this CH2 protons and signal B for the CH protons. So I have two signals A and B. So now these two signals are not as a single line, they come as a multiplet. So here the signals of the CH2 is coming like a doublet and the signals of CH is coming like a triplet. So you can see here. So CH2 comes like a doublet and the CH comes like a triplet. Now the question arises why it is so. Generally, the spin splitting occurs between two non-equivalent protons. So keep this in mind. So I have spin splitting only between non-equivalent protons, chemically equivalent protons. Keep that in mind. Chemically equivalent protons. Those who give the same signal, chemically equivalent protons, do not split each other. They do not split each other. Keep this in mind. Let us consider the example of this trihalo derivative. This molecule gives you a doublet and triplet. So as I told, CH2 gives you a doublet and CH gives you a triplet. In order to look into the details of this splitting, let us see a simple example. So in the absence of any adjacent hydrogens, the proton feels only this particular B0 field. There is no other field felt by it. So the signal is a single peak and you get a singlet for this particular proton with no adjacent hydrogens. But if I have one adjacent hydrogen, if I have one adjacent hydrogens, the absorbing hydrogen feels two different field. Look at this particular picture. So this is the B0, this is B0, and now the field of the adjacent protons can be either opposing the B0 or it can be aligning the B0. So on overall, I'll be experiencing two different fields. Here the neighboring proton's spin is opposing. So the neighboring proton, the spin is opposing the external field. Therefore, the field felt will be less and such field will shield the hydrogen under question, and the second is aligning with the external field for the field felt will be more and that will result in de-shield. So the proton under question will experience two different field, so field 1 and field 2. So this is a lesser field and this is a higher field. So I'll be having two different field around me. Therefore, I'll be split into two signals. So this is known as doublet. And now, since I'll experience only 1:1 ratio of this particular field, because I can have the second spin, that is adjacent spin can be either opposing or it can be aligned. So I can have only two probability. Therefore, the ratio of appearance of the doublet will be 1:1. Okay, so if I have one adjacent protons, the proton signals under question will be split into a doublet. So if I have Ha proton and Hb proton, so the A proton looks into the Hb proton. The Hb proton can either oppose the external field or it can align with the external field. So the A proton sees two spin polarization of B. So the spin is polarized down, that is, it is opposing the external field. It can polarize up, which is aligning with the external field. So I'll be experiencing, so A will be experiencing two different fields by the B proton. So two different environment. That is why A will be split into a doublet. So the frequency difference between this doublet is measured in hertz and it is known as the coupling constant J. Suppose I have two neighboring hydrogens. I have two adjacent hydrogens. So I have an hydrogen A and I have two adjacent B hydrogens. So now the B hydrogens, there are two B hydrogens. Therefore, both the B hydrogens can either oppose the external field, they can align with the external field, or they can either align or oppose. Align or oppose. oppose. Now suppose A opposes, the B opposes, A and B aligning, and I can have one aligning, one opposing. That is, A can have A aligning or A opposing, or I can have B aligning and B opposing. So I can have three probability, and the appearance of the ratio or appearance of the signal will be 1 is to 2 is to 1. Okay, so you can see both A and B can oppose the external field. So this is the external field here, so they both can oppose or they both can align, or A can oppose, B can align, or A can align and B can oppose. So I'll be feeling three different magnetic fields around me. So both are opposing, I'll be shielded. Both are aligning, I'll be de-shielded to an extreme extent. And one aligning, one opposed will be intermediate between both aligned and both opposite. So I'll experience three different fields, three different magnetic fields. I'll be split into a triplet. I'll be split into a triplet with a ratio of 1 is to 2 is to 1, and the distance between the lines of the multiplet. Keep in mind, it is a distance between the adjacent line of the multiplet, which is given as J, the coupling constant in Hertz. Now, there are general rules for splitting. So, keep in mind, they are very important, very important. The first rule is equivalent protons do not split each other. So, if they are chemically equivalent, they will not split each other. Then, if I have a set of n non-equivalent protons beside me, so I have n adjacent protons, so the signals will be split into n plus 1 peak. So a set of n non-equivalent protons splits the signals of a nearby proton into n plus 1 peak. So I'll be split into n plus 1 peak. So I have a proton and I count the number of b protons on either side. So if I have here, I have a b proton, here I have a b proton. So I'll be having two b protons. So my neighbor will be 2. So I'll be split into 2 plus 1. I'll be split into a triplet. So I'll be observing n plus 1 rule, and this is possible only for the set of n non-equivalent protons. Keep that in mind because equivalent protons will not split each other. So the splitting is observed for non-equivalent protons on same carbon or adjacent carbons. Now you will be surprised. So suppose I have A and B on the same carbon, then also I can have splitting. So this is known as geminal splitting. Do you remember when we were speaking about the chiral carbon and diastereotopicity of the ligands? Chiral carbon induces the chirality in a molecule and there will be no plane of symmetry. So the geminal protons will become chemically non-equivalent and they can split each other. So you can take an example. This is a geminal splitting. Or I can have in the adjacent carbons, which is known as the vicinal protons. So I can have the geminal protons splitting each other if they're chemically non-equivalent. This is known as geminal coupling constant or known as 2J coupling because they are two bond away, 1, 2. So A is splitting B or B is splitting A and they are two bond away. So it is two bond coupling. Whereas vicinal protons, A is split by B protons and they are three bond away. This is known as vicinal coupling, 3J coupling. Now, for a given number of neighboring protons, I'll be having n plus 1 peak. So, if I have no neighbors, n is equal to 0, so n plus 1 will be 1. So, I'll be having a singlet. If I have one neighbor, I'll be split into doublet. If I have two neighbors, I'll be split into triplet. If I have three neighbors, I'll be split into quartet. If I have four neighbors, I'll be split into quintet or pentet. If I have five neighbors, I'll be split into sextet. If I have six neighbors, I'll be split into septet. And if I have more than seven, I'll be split into a multiplet. Multiplet is given as M. So generally, we give singlet as S, doublet as D, triplet as T, quartet as Q. So these are the most often observed splitting patterns. So you can see here the A protons have two neighboring B protons. So you can see here the A proton has one neighboring B proton and the B proton has one neighboring A proton. So A has n plus 1. So 1 plus 1, so doublet. Again B has 1 plus 1, so B is also doublet. Now here A has two B protons, so A will be having 2 plus 1. So A will be a triplet. And B has only one neighbor, therefore 1 plus 1, so B will be doublet. So here the A protons have two B protons, so 2 plus 1, so I'll be having triplet. And B has again two A protons, so it will be again 2 plus 1, it will be also a triplet. Coming to the fourth one, I have A protons having 3 B protons. So 3 plus 1, I'll be split as quartet. So A will be split as quartet. Now B has 2 A protons. So 2 plus 1. So B will be split as a triplet. Last one, I have A proton and B proton. The A proton has 3 neighboring protons. So 3 plus 1, the A proton will be split as quartet. And B proton has only one neighboring proton. Therefore, the B will be split as a doublet. 1 plus 1 will split as a doublet. Now, if I have three neighboring protons, so if I have three neighboring protons, I'll be split as 3 plus 1. I'll be split into a quartet. Now, quickly we can say the intensity ratio of this quartet will be like I have three protons, all the three protons, neighboring protons can oppose, or all the three can align with the external field, or I can have two opposing, one aligning. So the A can oppose, B can oppose, C can align. So if I have A, B, C, A, B, C, all the three are opposing, A, B, C, all the three are aligning. So here A, B, C, two can oppose, one can align. So I can have three such situations. I can have three such situations. Similarly, I can have the A can oppose, the B and C can align. So A, B, C. So I can have again three such situation. I can have three such situation. So the intensity ratio is 1 is to 3 is to 3 is to 1. So likewise, I can go on with the next number of protons, the neighboring protons. But doing this will take lot of time. So in order to find the intensity ratio of multiplets, we can use something known as Pascal's triangle. Pascal's triangle. So Pascal's triangle, I start with 1. So I have no neighbors. N0, I have no neighbors. So now if I have one neighbor, I'll be split into a doublet. Doublet will be intensity of 1 is to 1. Then if I have two neighbors, I'll be split into triplet. 1 is to 2 is to 1. If I have three neighbors, I'll be split into quartet with the intensity ratio of 1 is to 3 is to 3 is to 1. So 1 gives you 1, 1 plus 1 is 2 and 1. Now here I have 1, then 1 plus 2 is 3, this 2 plus 1 is 3 and 1. Now if I have 4 neighboring protons, I'll be split as 1. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4 and 1. So if I have 4 neighboring protons, the intensity ratio will be 1 is to 4 is to 6 is to 4 is to 1. So likewise, you can just go on. Okay. Whenever two or three different sets of adjacent protons are equivalent. So I have different sets of protons, but they are equivalent. So here I'll use n plus 1 rule and I'll add all the neighboring protons. So I have 6 neighboring protons for the CH. So CH, so I have two types of signal here, A signal for CH and B signal for the CH3. So I have 6 B protons and I have one A proton. So A proton sees 6 B protons. So it will be split into 6 plus 1, 7, which is septet. It is septet. You can see it septet. So 1, 2, 3, 4, 5, 6, 7. Septet. 7. So multiplet is a septet. 7 lines. And B will be seeing the A proton. You have only one A proton. So 1 plus 1 B will be split into a doublet. It will be split into a doublet. So I'll be having a doublet. Easy, isn't it? So when I talk about the OH protons, so under usual condition, OH proton does not split the NMR signal of the adjacent protons. So the signal due to an OH proton is not split by the adjacent proton. So OH will neither split the signals of the adjacent proton nor it will be split by the adjacent protons. Now why is that? So the OH protons, the NH protons and the carboxylic acid protons. They are known as exchangeable protons. Exchangeable protons. So they are in constant exchange with the solvent molecules or the acid present, small amount of acid or or a very minute amount of base. If it is present, that will be in constant exchange with them. So due to this constant exchange, they are not absorbed by the neighboring protons. So the protons will not be lying in one particular place to be absorbed by the neighboring protons to undergo splitting. So they'll be in constant exchange with the solvent acid base molecule. So they'll be not available for coupling, spin spin splitting or spin spin coupling. So generally this C, that is OHC, it will remain as a singlet. It will remain as a singlet. So neither it will be split by the neighboring protons nor it will split the neighboring protons. So the CH2, the B protons neighboring only 3 CH3 protons you consider. So 3 plus 1. So CH2 is split into a quartet. Similarly, the A has 2 neighboring protons, therefore 2 plus 1 CH2 is split into a triplet. Is that okay? So ethanol has 3 different types of protons. So there are 3 signals. The A proton is split by 2 B protons into 3 peaks, that's triplet. And B signal is split by 3 A protons into 4 peaks, it's a quartet. The adjacent OH proton does not split the signal of HB or nor it is split by this presence of HB. Okay, so HC is a singlet because OH protons are not split by the adjacent protons. So the protons on an electronegative atoms, that is OH, NH, carboxylic acid OH, are rapidly exchanging between the molecules in the presence of trace amounts of acid or bases. Thus, the CH2 group never feels the presence of the OH proton. That is what I was talking about, because the OH proton is rapidly moving from one molecule to the another. It's rapidly moving from one molecule to the another. This phenomenon usually occurs in NH, OH, and as I told you, I'll be having carboxylic acid. Generally, this will give rise to a broadening of peak. So, if you have broader peak, you can be sure that you have this exchangeable hydrogens. I can even find them by exchanging them with the deuterated water. So, on exchange, I'll be getting O deuterium plus HOD peak. I've already mentioned this in the previous video, and this HOD peak will come around 4.5 delta. So presence of HOD peak also talks about the presence of an exchangeable hydrogen. Now protons on the aromatic ring, benzene ring, they have a delta value of 7.2 ppm. So now a mono substituted benzene, here you'll be having 5 different kinds of protons. So just take this clue. If you have a signal saying you have 7.65 hydrogen multiplet, keep in mind that the 5 hydrogens are left and one hydrogen is substituted, therefore it is mono substituted benzene. Important clue. Important clue. If a value says that you have 4 hydrogen signal they have given, that is 7.22 hydrogen and 6.92 hydrogen, so aromatic region 4 hydrogens are left unsubstituted, so that shows that 2 hydrogens are substituted. So it is a disubstituted benzene ring. Keep this in mind, very very important. Okay, so likewise, if you have 3 hydrogen, they are giving the signals, so that shows that other 3 hydrogens are substituted, that shows it's tri-substituted. Okay, so if I have an alkyl group, so generally what will happen, the 5 aromatic protons will be having an accidental equivalence, so they'll appear at almost similar values. So you can see here they are like coalesced with each other. But when I have an aldehyde electron withdrawing group, they are the minus R group. In such cases, I'll be having splitting pattern. And when I have OCH3, which is the plus R group, I'll be having the splitting pattern. So the splitting of signals for the non-equivalent protons, that is A, they are orthoprotons, B, they are the metaprotons, and C, it is the paraprotons. So 3 kinds of protons, because I can cut the molecule like this. So A and A are equivalent, B and B are equivalent, and C is the different protons. So I'll be having 3 different types of protons, and these protons will be coming as splitting. So they can be like sometimes it will come like a multiplet, and sometimes they will come like a, for A will be giving you a doublet, B will be giving you a triplet, and C will be giving you a triplet. So I'll be having splitting of signals giving you the different signals for different protons. Now here I'd like to touch upon one important thing which is usually asked in an problem solving. So suppose I have the para substituted benzene ring. So I'll be having four hydrogens which will be left, four hydrogens will be left. And since in this molecule I have a plane of symmetry, I can cut the molecule like this. So this A and A protons will be equivalent, this B and B protons will be equivalent. So I'll be having only two proton signals, A proton and B proton, and the splitting will be A has one neighboring proton, so 1 plus 1. So A will come as a doublet, and B has one neighboring proton, A proton, only one A proton, therefore B will be coming as a doublet. So when I have doublet and doublet, they say doublet 2 hydrogen, doublet 2 hydrogen in your data, NMR data. So doublet and doublet means you should straight away say that's paradise substituted. So this is a very important clue in solving the NMR problem. So when I have a meta di substituted, so you know that you have four signals A, B, C and D. So we'll be having four signals. We will be having a singlet, a doublet, a triplet, and a doublet. So when you have doublet and doublet, be sure that you have the para isomer. Ortho isomer will also give you more number of signals. So when I take the ortho isomer, four different types of proton: doublet, triplet, triplet, and doublet. So more number of signals. While talking about spin splitting, so I can have splitting between the hydrogens which are present on the same carbon. So here I have taken the hydrogens which are present on the same carbon known as geminal hydrogens. So now these geminal hydrogens will be having a coupling constant which is very low, around 0 to 3. Whereas when I have the vicinal coupling, so between the adjacent hydrogens, I told you already 3J coupling. This is known as 2J coupling. So now this 3J coupling will be like I can have the two hydrogens on an alkene. They are diastereomeric, so they'll be having the hydrogens which are cis to each other and the hydrogen which are trans to each other. Now this is also 3J coupling. So you can see one bond, two bond, three bond. This is also one bond, two bond, three bond. They both are vicinal coupling, but this has a value of 5 to 10 hertz and this has a value of 11 to 18 hertz. So the trans coupling constant is having higher value compared to the cis coupling. So in the 3J, the trans has greater value than the 3J cis, which is greater than the 2J geminal. So now I have to find the reasons for such thing. Okay, so the protons and carbon-carbon double bonds give different splitting patterns. So the double bonds can have two geminal protons and two cis protons or two trans protons. So now the magnitude of this coupling constant depends upon the arrangement of hydrogen atoms. So they are, whether they are geminal, they'll be having one value. They are cis, they'll have another value, and if they are trans, they'll be having another value. Now I can see that in this particular example, the E isomer, I've got the trans, so the coupling constant value is 14. So A proton split by the B proton and the B proton split by the A proton. So I have two different doublets and they have the coupling constant of 14. So this is the distance between the lines of multiplet. So A split by B or the B split by A, they both are same. So I'll be having 14 hertz. Whereas here the A and B assist to each other, they'll be having only 8 hertz. So now we have to find the reason for this particular thing. In order to solve the confusion which arises why the cis coupling is greater than trans coupling, we have to look into the Karplus equation. So Karplus has given a mathematical equations and he has solved the mathematical equations to get the relationship between the 3J coupling and the dihedral angle theta. So Karplus gives a theoretical relationship between the coupling constant, 3J coupling constant and the dihedral angle. So now as we can see here, if the dihedral angle is 90, it has the lowest J value. The 3 And when the dihedral angle is 180, the 3J coupling constant is the highest. And then comes the 3J coupling constant for a dihedral angle of 0 degrees. So this is the dihedral angle. Okay, so you have the carbon carbon. So just imagine you have an open notebook. So the central line of the notebook will be the CC bond, and one side of the plane will be having CH, the other side will be having the other hydrogen. So now if I close the notebook, the theta will become equal to 0. If I completely open the notebook on and keep it flat, then the theta becomes 180 degrees. And when I keep the two sides of the notebook in 90 degrees perpendicular, then the theta becomes 90 degrees. So now when I have theta 180, this dihedral angle is 180, I'll be having the highest coupling constant compared to the theta of 0 degrees. And 90 has a minimum coupling constant. And the reason is, so when I have the theta equal to 180, that is anti-periplanar geometry, I'll be having the better interaction between the orbitals. So you can see the interaction, I'll better interaction, and that will give rise to a higher coupling between the two adjacent protons on the adjacent carbon compared to that of an ortho, that is I have cis coupling, that is the theta is equal to 0, the both the hydrogen on the same plane. So now I'll be having good interaction, but when I have 90 degrees, there is no coupling, there is no interaction between the orbitals. So that will be having the poor interaction, that will give the lowest J value. So 180 will be highest, then comes 0, and then comes the 90. So we say to be anti-periplanar geometry between the two hydrogens. I get syn periplanar between the two hydrogens. This is known as orthogonal. 90 degrees, I said to be orthogonal. So anti has the highest, then comes cis or syn, and then last is orthogonal. So the factors other than the dihedral angle is the electron density at the carbons of the CH2 or CH group. So if I have higher electron density, I'll be having higher coupling constant, because I we should know that when I have the information passed from A to B, I should know whether A is having upward spin or downward spin. So the spin information of B, whether it's upward or downward, is passed to the A through the bonds. That is the electrons connecting the bonds between the two hydrogens. So electrons play a very important role. So if I have more number of electrons, I'll be having a perfect polarization transfer, information transfer. So the information of the spin polarization of B to A. So A is looking at B. So B is either upward or downward. This information is passed to the bonds, and the electrons of the bond are the one which are required for passing the information or spin polarization information. So if I have high electron density, I'll be having the better coupling compared to low electron density. So if I have high electron density, I'll be having better coupling constant. So you can see lithium is electron donating. I have high coupling constant, and I have the OE2 plus. So it is highly electron withdrawing. I'll be having low coupling constant. So you can, as I move from left hand side to the right hand side, I have electron withdrawing group is increasing, so the coupling constant is decreasing. Now that can be reflected also here. So I have electron donating group, and now I have, this is the geminal coupling, and these is known as cis coupling, 3J cis, and this is known as the 3J trans. So 3J trans is having the higher value, and 3J cis has the lower value. Now compare this with the last molecule. Fluorine is electron withdrawing. So obviously the trans has the higher value and the cis has the lower value, but the value comparison between these two molecules is drastically varying. So here I have 23.9 for trans, here I have 12.8 for trans. Why this is happening? Because along with the dihedral angle, I should also concentrate on the electron density around the coupling partners. Hope you have understood this concept very clearly. So if you have any doubts, just kindly post that in the comment section.